Okay, and so here's just a summary of the convolutional layer that you guys can read a little bit more carefully later on. But we have our input volume of a certain dimension. We have all these we have our filters, right, where we have number of filters, the filter size, the stride of the size, the amount of zero padding, and you basically can use all of these, go through the computations that we talked about earlier in order to find out what your output volume is actually going to be and how many total parameters that you have. And so some common settings of this, we talked earlier about common filter sizes of 3 by 3, 5 by 5. Stride is usually 1 and 2 is pretty common, and then your padding P is going to be whatever fits, like whatever will preserve your spatial extent is what's common. And then the total number of filters K. Usually we use powers of 2 just to be nice, so 32, 64. 128, and so on, 512. These are pretty common numbers that you'll see. And just as an aside, we can also do a 1-by-1 convolution. This still makes perfect sense, where given a 1-by-1 convolution, we still slide it over each spatial extent, but now the spatial region is not really 5 by 5. It's just kind of the trivial case of 1-by-1, but we are still having this filter go through the entire depth. Right, so this is going to be a dot product through the entire depth of your input volume. And so the output here, right, if we have an input volume of 56 by 56 by 64 depth, and we're going to do 1-by-1 convolution with 32 filters, then our output is going to be 56 by 56 by our number of filters, 32. Okay, and so here's an example of a convolutional layer in Torch, deep learning framework. And so you'll see that last lecture we talked about how you can go into these deep learning frameworks. You can see these definitions of each layer, right, where they had kind of the forward pass and the backward pass implemented for each layer. And so you'll see spatial convolution is going to be just one of these. And then the arguments that it's going to take are going to be all of these design choices of your input and output sizes, but also your choices of like your kernel width, your kernel size, padding, and these kinds of things. Right, and so if we look at another framework, Caffe, you'll see something very similar, where again, now when you're defining your network, you define networks in Caffe using this kind of proto-text file where you're specifying each of your design choices for your layer, and you can see for a convolutional layer, we'll say things like the number of outputs that we have. This is going to be the number of filters for Caffe, as well as the kernel size and stride and so on. Yeah, so the question is, what's the intuition behind how you choose your stride? And so at one sense, it's kind of the resolution at which you slide it on. And usually the reason behind this is because when we have a larger stride, what we end up getting as the output is a downsampled image, right? And so what this downsampled image lets us have is, both, it's kind of like pooling in a sense, but it's just a different and sometimes works better way of doing pooling, is one of the intuitions behind this, right? Because you get the same effect of downsampling your image. And then also, as you're doing this, you're reducing the size of the activation maps that you're dealing with at each layer, right? And so this also affects later on the total number of parameters that you have, because, for example, at the end of all your conv layers, now you might put on fully connected layers on top, for example, and now the fully connected layer is going to be connected to every value of your convolutional output, right? And so a smaller one will give you smaller number of parameters, and so now you can get into like basically thinking about trade-offs of number of parameters you have, the size of your model, and overfitting, things like that. And so yeah, these are kind of some of the things that you want to think about with choosing your stride. Okay, so now if we look a little bit at kind of the brain neuron view of a convolutional layer, similar to what we looked at for the neurons in the last lecture. So what we have is that at every spatial location, we take a dot product between a filter and a specific part of the image, right? And we get one number out from here. And so this is the same idea of doing these types of dot products, right? Taking your input, weighting it by these W's, right? Values of your filter, these weights that are the synapses, and getting a value out. But the main difference here is just that now your neuron has local connectivity. So instead of being connected to the entire input, it's just looking at a local region spatially of your image. And so this looks at a local region, and then now you're going to get kind of, this how much this neuron is being triggered at every spatial location in your image, right? So now you preserve the spatial structure, and you can say, be able to reason on top of these kinds of activation maps in later layers. And just a little bit of terminology. Again, for we have this 5x5 filter. We can also call this a 5x5 receptive field for the neuron, because this is the receptive field is basically the input field that this field of vision that this neuron is receiving, right? And so so that's just another common term that you'll hear for this. And then again, remember, each of these 5x5 filters, we're sliding them over to the spatial locations, but they're the same set of weights. They share the same parameters. Okay, and so, as we talked about, like what we're going to get at this output is going to be this volume, right, where spatially we have, let's say 20 by 28, and then our number of filters is the depth. And so, for example, with 5 filters, what we're going to get out is this 3D grid that's 28 by 28 by 5. And so if you look at the filters across in, one spatial location of the activation volume and going through depth, these 5 neurons, all of these neurons, basically the way you can interpret this is they're all looking at the same region in the input volume, but they're just looking for different things, right? So they're different filters applied to the same spatial location in the image. And so just a reminder again, to, kind of comparing with the fully connected layer that we talked about earlier. In that case, right, if we look at each of the neurons in our activation or output, each of the neurons was connected to the entire stretched out input. So it looked at the entire full input volume compared to now where each one just looks at this local spatial region. Okay, so we've gone into a lot of detail on what these convolutional layers look like. And so now I'm just going to go briefly through the other layers that we have that form this entire convolutional network, right? So remember, again, we have convolutional layers interspersed with pooling layers once in a while, as well as these nonlinearities. Okay, so what the pooling layers do is that they make the representations smaller and more manageable, right? So we talked about this earlier with someone asked a question of why we would want to make the representation smaller. And so this is, again, to have fewer, it affects the number of parameters that you have at the end, as well as basically does some invariance over a given region. And so what the pooling layer does is it does exactly just downsamples, and it takes your input volume, so for example 224 by 224 by 64, and spatially downsamples this. So in the end you'll get out 112 by 112. And it's important to note this doesn't do anything in the depth, right? We're only pooling spatially. So the number of your input depth is going to be the same as your output depth. And so, for example, a common way to do this is max pooling. So in this case, our pooling layer also has a filter size, and this filter size is going to be the region at which we pool over, right? So in this case, if we have 2 by 2 filters, we're going to slide this, and so here we also have stride 2 in this case. So we're going to take this filter and we're going to slide it along our input volume in exactly the same way as we did for convolution. But here, instead of doing these dot products, we just take the maximum value of the input volume in that region, right? So here, if we look at the red values, the value of that will be 6 is the largest. If we look at the greens, it's going to give an 8, and then we have a 3 and a 4. Yes, question? Yeah, so the question is it typical to set up the stride so that there isn't an overlap? And yeah, so for the pooling layers, it is, I think the more common thing to do is to have them not have any overlap. And I guess the way you can think about this is, basically we just want to downsample, and so it makes sense to kind of look at this region and just get one value to represent this region, and then just look at the next region and so on. Yeah, question? So the question is, why is max pooling better than just taking the doing something like average pooling? Yes, that's a good point. Like, average pooling is also something that you can do. And the intuition behind why max pooling is commonly used is that you can have this interpretation of, if this is, these are activations of my neurons, right? And so each value is kind of how much this neuron fired in this location, how much this filter fired in this location. And so you can think of max pooling as saying, giving a signal of how much did this filter fire at any location in this image, right? And if we're thinking about detecting, doing recognition, this might make some intuitive sense where you're saying, well, whether a light or whether some aspect of your image that you're looking for, whether it happens anywhere in this region, we want to fire at with a high value. A question? So the question is, since pooling and stride both have the same effect of downsampling, can you just use stride instead of pooling and so on? Yeah, and so in practice, like, I think looking at more recent neural network architectures, people have begun to use stride more in order to do the downsampling instead of just pooling. And I think this gets into things like, also like fractional strides and things that you can do. But in practice, this in a sense maybe has been a little bit better way to get better results using that. So yeah, so I think using stride is definitely, you can do it, and people are doing it. Okay, so let's see, where were we? Okay, so yeah, so with these pooling layers, so again, there's some design choices that you make. You take this input volume of W by H by D, and then you're going to set your hyperparameters for design choices of your filter size, right, the spatial extent over which you're pooling, as well as your stride. And then you can again compute your output volume using the same equation that you used earlier for convolution. It still applies here, right? So we still have our W total extent minus filter size divided by stride plus 1. Okay, and so just one other thing to note, it's also, typically people don't really use zero padding for the pooling layers because you're just trying to do a direct downsampling, right? So there isn't this problem of like applying a filter at the corner and having some part of the filter go off your input volume. And so for pooling, we don't usually have to worry about this, and we just, directly downsample. And so some common settings for the pooling layer is a filter size of 2 by 2 or 3 by 3, strides 2 by 2. You can have also, you can still have pooling of 2 by 2 even with a stride of even with a filter size of 3 by 3. I think someone asked that earlier, but in practice it's pretty common just to have 2 by 2. Okay, so now we've talked about these convolutional layers. The ReLU layers were the same as what we had before with the just the base neural network that we talked about last lecture. So we intersperse these, and then we have a pooling layer every once in a while when we feel like downsampling, right? And then the last thing is that at the end we want to have a fully connected layer, and so this will be just exactly the same as the fully connected layers that you've seen before. So in this case now what we do is we take the convolutional network output. We at the last layer we have some volume, so we're going to have width by height by some depth. And we just take all of these and we essentially just stretch these out, right? And so now we're going to get the same kind of, basically 1D input that we're used to for a vanilla neural network. And then we're going to apply this fully connected layer on top. So now we're going to have connections to every one of these convolutional map outputs. And so what you can think of this is basically now instead of preserving, before we were preserving spatial structure, right? And so, but at the last layer at the end, we want to aggregate all of this together, and we want to reason basically on top of all of this as we had before. And so what you get from that is just our, score outputs as we had earlier. Okay. Okay, so the question is, what are the 16 pixels that are on the far right? Do you mean the, oh, each column? The green ones or the black ones? The one with, hold on, pool. Oh, okay. Yeah, so the question is, how do we interpret this column, right, for example, at pool? And so what we're showing here is each of these columns is the output uh, activation maps, right? The output from one of these layers. And so starting from the beginning, we have our car. After the convolutional layer, we now have these activation maps of each of the filters slid over spatially over the input image. Then we pass that through a ReLU, so you can see the values coming out from there, and then going all the way over. And so what you get for the pooling layer is that it's really just taking the output of the ReLU layer that came just before it, and then it's pooling it. So it's going to downsample it, right? And then it's going to take the max value in each filter location. And so now if you look at this pool layer output, like for example, the last one that you were mentioning, it looks the same as this ReLU output, except that it's downsampled, and that it has this kind of max value at every spatial location. And so that's the minor difference that you'll see between those two. So the question is now, like, this looks like just a very small amount of information, right? So how can it know to classify from here? And so the way that you should think about this is that each of these values inside one of these pool outputs is actually, it's the accumulation of all the processing that you've done throughout this entire network, right? So it's at the very top of your hierarchy. And so each actually represents kind of a higher level concept. So we saw before, for example, Hubel and Weasel, and building up these hierarchical filters, where at the bottom level, we're looking for edges, right? Or things like very simple structures like edges. And so after your convolutional layer, the outputs that you see here in this first column is basically how much do specific, for example, edges fire at different locations in the image. But then as you go through, you're going to get more complex, it's looking for more complex things, right? And so the next convolutional layer is going to fire at how much, let's say certain kinds of corners show up in the image, right? Because it's reasoning, its input is not the original image, its input is the output, it's already, the edge maps, right? So it's reasoning on top of edge maps. And so that allows it to get more complex, detect more complex things. And so by the time you get all the way up to this last pooling layer, each value is representing how much a relatively complex, sort of template is firing, right? And so because of that, now you can just have a fully connected layer. You're just aggregating all of this information together to get, a score for your class. So each of these values is how much a pretty complicated, complex concept is firing. Question. So the question is, when do you know you've done enough pooling to do the classification? And the answer is you just try and see. So in practice, these are all design choices, and you can think about this a little bit intuitively, right? Like you want to pool, but if you pool too much, you're going to have very few values like representing your entire image, and so on. So it's just kind of a trade-off, something reasonable versus people have tried a lot of different configurations. So you'll probably cross-validate, right, and try over different pooling sizes, different filter sizes, different number of layers, and see what works best for your problem. Because like every problem with different data is going to, different set of these sorts of hyperparameters might work best. Okay, so last thing, just wanted to point you guys to this demo of training a ComNet, which was created by Andre Karpathy, the originator of this class. And so he wrote up this demo where you can basically train a ComNet on CFAR10, the data set that we've seen before, right, with 10 classes. And what's nice about this demo is you can, it basically plots for you what each of these filters look like, what the activation maps look like. So some of the images I showed earlier were taken from this demo. And so you can go try it out, play around with it, and just go through and try and get a sense for what these activation maps look like. And just one thing to note, usually the first layer activation maps are, you can interpret them, right? Because they're operating directly on the input image, so you can see what these templates mean. As you get to higher level layers, it starts getting really hard, like how do you actually interpret what do these mean? So for the most part, it's just hard to interpret, so you shouldn't, don't worry if you can't really make sense of what's going on, but it's still nice just to see the entire flow and what outputs are coming out. Okay, so in summary, so today we talked about how convolutional neural networks work, how they're basically stacks of these convolutional and pooling layers, followed by fully connected layers at the end. There's been a trend towards having smaller filters and deeper architectures. So we'll talk more about case studies for some of these later on. There's also been a trend towards getting rid of these pooling and fully connected layers entirely. So just having conv layers, very deep networks of conv layers. So again, we'll discuss all of this later on. And then typical architectures again look like this. As we had earlier, conv ReLU for some n number of steps, followed by a pool every once in a while. This whole thing repeated some number of times, and then followed by fully connected ReLU layers that we saw earlier, one or two or just a few of these, and then a softmax at the end for your class scores. And so, some typical values, you might have n up to 5 of these. You're going to have pretty deep layers of conv ReLU pool sequences, and then usually just a couple of these fully connected layers at the end. But we'll also go into some newer architectures like ResNet and GoogleNet, which challenge this and will give pretty different types of architectures. Okay, thank you, and see you guys next time.
지금까지 배운 컨브 레이어를 요약하면 다음과 같습니다. 볼륨 사이즈는 W1, H1, D1을 어셉트합니다. 4개의 하이퍼 파라미터는 다음과 같습니다. Number of filter K, Special Extent F, Stride S, Zero Padding P입니다. 이를 통해서 W2, H2, D2의 볼륨을 프로듀스합니다. 각 필터에는 F 곱하기 F 곱하기 D1의 웨이트와 한 개의 바이어스가 필요합니다. K 값으로는 대개 2의 파워가 사용됩니다. 즉 32, 64, 128, 512 등의 숫자가 사용됩니다. 필터의 F 값은 3, 5, 1 등의 숫자가 사용되고 스트라이드와 패딩은 이에 따라 조절될 수 있습니다. 다음은 원바이원 컨볼루션 레이어의 특수한 경우입니다. 각각의 필터는 1 곱하기 1 곱하기 64의 크기를 가질 수 있고 64 디멘전의 더 프로덕트를 수행합니다. 이러한 필터들이 32개가 있을 경우 액티베이션 맵이 32개가 만들어집니다. 컨브 레이어를 브레인과 뉴런의 관점에서 살펴볼 수도 있습니다. 필터는 이미지 전체를 이동하면서 5 곱하기 5 곱하기 3의 75 디멘셔널 더 프로덕트를 수행해서 하나의 값을 계산해냅니다. 이것은 우리가 퍼셉트론 모델에서 사용했던 로컬 커넥티비티를 가진 뉴런에 대응하는 것입니다. 여기서 액티베이션 맵은 뉴런 아웃풋에 28 곱하기 28의 시트로 생각할 수 있습니다. 각각은 인풋의 작은 리전에 연결되어 있습니다. 그리고 모든 것들은 파라미터를 쉐어합니다. 따라서 5 곱하기 5 필터는 5 곱하기 5의 각각의 뉴런에 대한 리셉티브 필드로 생각할 수 있습니다. 주어진 그림처럼 5개의 필터가 있다면 컨브 레이어는 뉴런들이 28 곱하기 28 곱하기 5의 3D 그리드로 어레인지 되어 있다고 볼 수 있습니다. 이것은 5개의 뉴런들이 인풋 볼륨에서 같은 리전을 보고 있다고 해석할 수 있습니다. Fully Connected 레이어를 다시 리마인드하면 인풋 이미지를 3072 곱하기 1의 벡터로 스트레치한 뒤 각각의 뉴런이 전체 인풋 볼륨을 볼 수 있도록 한 것입니다. 반면에 컨브넷은 전체 이미지를 이동해 가면서 한 번에 일부의 이미지만 보도록 한 것입니다. 다음은 컨볼루셔널 뉴럴 네트워크에서 풀링이 어떻게 동작하는지에 대해서 알아보도록 하겠습니다. 풀링은 다운샘플링을 통해서 레프레젠테이션을 더 작고 매니저블하게 만듭니다. 각각의 액티베이션 맵에 독립적으로 작용합니다. 다음은 맥스 풀링의 사례입니다. 왼쪽에는 4x4의 싱글 데프트 슬라이스가 있고 오른쪽에는 2x2의 맥스 풀링의 아웃풋이 있습니다. 여기서 숫자 6은 1156 중에서 맥시멈을 취한 것이고 숫자 8은 2478에서 맥시멈을 취한 것입니다. 맥스풀에는 2x2 필터에 스트라이드 2가 적용되었습니다. 맥스풀링을 요약하면 다음과 같습니다. 인풋 볼륨 사이즈는 W1, H1, D1이라고 할 때 하이퍼 파라미터는 스페셜 익스텐트 F와 스트라이드 S입니다. 그 결과 W2, H2, D2의 볼륨을 프로듀스합니다. 맥스 풀링 레이어는 컨볼 레이어와 달리 웨이트와 바이어스 파라미터를 필요로 하지 않는다는 것에 주목할 필요가 있습니다. 맥스 풀링에서 흔히 사용되는 세팅으로 필터 F는 2, 스트라이드는 2, F3, SE 등이 있습니다. 제로 패딩은 거의 사용되지 않습니다. 마지막 단계에서는 Fully Connected 레이어가 사용됩니다. 우리가 이전에 배웠던 Fully Connected 레이어와 같은 개념입니다. 다음은 스탠포드에서 제공하는 컨볼루셔널 뉴럴 네트워크의 데모입니다. 아래 웹사이트 주소로 가시면 트레이닝 과정이 여러분의 브라우저에서 수행되는 것을 관찰하실 수 있습니다. 서머리입니다. 컨볼루셔널 뉴럴 네트워크는 컨볼 레이어, 풀 레이어, 폴리 커넥티드 레이어 등으로 이루어질 수 있습니다. 더 작은 필터와 디퍼 아키텍처의 트렌드가 있습니다. 풀과 FC 레이어를 없애고 컨볼 레이어만으로 구성하는 아키텍처의 트렌드도 있습니다. 전형적인 아키텍처는 다음과 같습니다. 컨볼 레이어와 밸류 레이어가 n개 있을 때마다 풀 레이어는 1개씩 있습니다. 이때 n값은 1개부터 5개까지 변할 수 있습니다. 또한 이 전체가 m개 있을 수 있는데 m값은 수십 개가 될 수도 있습니다. 마지막에는 FC와 밸류 레이어가 0개, 1개 혹은 2개가 있고 소프트맥스가 있을 수 있습니다. 최근의 발전을 보면 레즈넷이나 구글 에셋처럼 이러한 패러다임은 변할 수 있습니다.